Hello, my name is Liz Rampey, and I'm an exploration mission scientist in the Astromaterials Research and Exploration Science, or ARES division at the NASA Johnson Space Center in Houston, Texas. And I'm going to talk to you about the Mars Science Laboratory Curiosity mission in Gale Crater. And specifically, I'll tell you about results from ChemIn and SAM that help us constrain past aqueous environments and habitability of Gale Crater. I'm going to focus on the results from these instruments in particular, because many of us scientists in ARES are deeply involved in the operations and also the interpretations of the results from these two instruments. I'm the deputy principal investigator of the ChemIn instrument. We also have two co-investigators and three collaborators within ARES from ChemIn. And for the SAM team, we have three co-investigators and two collaborators within ARES. So since I'm the deputy principal investigator of ChemIn, I'm really going to focus on the mineralogical results from that instrument, but I'll also talk a little bit about some of the SAM results. So Curiosity landed in Gale Crater in August 2012 with the goal of studying the habitability, either past or present, of this local region on Mars. Gale Crater is an impact basin. It's about 150 kilometers in diameter, and in the middle there's this mound of layered sedimentary rock called Mount Sharp. And Curiosity landed in Gale Crater because we know from orbital visible near-infrared reflectance spectroscopy that some of the layers in the lower foothills of Mount Sharp show evidence for minerals that formed from water-rock interactions. And life as we know it requires liquid water. So if we zoom into these lowermost layers of Mount Sharp, we see that some of these layers have spectral signatures of minerals like hematite, which is an iron 3+ oxide, clay minerals, specifically iron magnesium smectite, and also sulfate salts. So the goal for Curiosity was to drive up these layers, studying their sedimentology and their composition to determine what these ancient environments were like and if they would have been habitable to ancient microbial life. Curiosity has a variety of science instruments to study these surface rocks and sediments and also the modern environment. But again, I'm going to focus on the results from ChemIn and SAM, which are our two internal laboratories. ChemIn stands for Chemistry and Mineralogy. We perform X-ray diffraction with this instrument, and so the results from ChemIn tell us about the minerals that are present in either drilled rock samples or scooped sediments, and we can detect minerals down to a detection limit of about 1%. Minerals in these samples, or determining the minerals, is crucial for understanding past aqueous environments, because there are some minerals that form under very specific aqueous conditions of pH, temperature, salinity, and redox. SAM stands for the Sample Analysis at Mars. It is a combination gas chromatograph, mass spectrometer, and tunable laser spectrometer. SAM can determine the volatile content in samples, and it can also identify organic molecules. With the volatile content, that allows us to further constrain the minerals present in these samples, and organic molecules are the building blocks for life. So the identification of those molecules suggests that they would have been available for microorganisms on early Mars if they existed. This shows you our traverse from our landing site on the plains of Gale Crater to our current location today up on the foothills of lower Mount Sharp. We've driven about 23 kilometers in the last 8 years or so. All of the outcrops that we've encountered have been sedimentary in nature, and most of them were deposited by rivers and lakes about 3.5 billion years ago. We have drilled 29 rocks and scooped 3 loose sediments to date, and we've analyzed all of those samples with ChemIn, and most of them with SAM. And these circles just show you where we either drilled rocks or scooped loose sediments. But today I want to focus on the most recent results from the mission, and I'm going to start with our campaign on this resistant ridge here. The first unit that Curiosity investigated that had a strong mineralogical signature from orbit is a feature that we called Vera Rubin Ridge, named after the famous astronomer. And Vera Rubin Ridge has a signature from orbit for the mineral hematite, which is an iron 3+ oxide. And these red and yellow colors show you where that signature for hematite is the strongest. Hematite forms from water-rock interactions, and the mineralogy, or the bulk mineralogy of samples from the ridge, can help us further constrain the environments in which this hematite precipitated. So this yellow line shows you our traverse up and along Vera Rubin Ridge. We drilled 3 samples from on the ridge and 1 just below the ridge, and analyzed those samples with ChemMin and SAM. These pie diagrams show you the mineral abundances and X-ray amorphous abundances for those 4 samples, where every mineral is represented by a different color. Hematite is in these red slices of pie. You can see that all of the samples contain hematite, and in fact this sample named Stower has the most hematite of any sample that we have drilled to date. Most of these rocks that we drilled, or many of them, were red in color, and fine particulates of hematite are red, which helps give Mars its red color. But we also found some gray rocks up on Vera Rubin Ridge, and this is an example of the drill hole from High Field. But you'll see that High Field also contained abundant hematite, suggesting the presence of gray hematite. Gray hematite has a slightly larger particle size than red hematite, and on Earth it commonly forms under elevated temperatures of about 100 degrees C. So the discovery of gray hematite on Vera Rubin Ridge suggests that some of the groundwaters that interacted with Vera Rubin Ridge were fairly warm. We also see some other interesting indicator minerals. In purple, this is jarosite. This is an iron 3+ sulfate. In pink is akagonite, which is an iron 3+ oxyhydroxide with chlorine in its structure. Jarosite forms under acid sulfate conditions, and well-crystalline akagonite, like we see with ChemMin, forms under acid saline conditions. So the identification of these 2 minerals in a couple of samples suggests that some of the fluids that interacted with Vera Rubin Ridge were also acidic. So after our campaign on Vera Rubin Ridge, which you can see here on the upper left, we descended the ridge to the south into this local valley that we called Glen Torridin. And from orbit, we know that Glen Torridin has a signature of iron magnesium smectite. This purple line shows our traverse through Glen Torridin, and these arrows show you where we drilled samples and delivered them to ChemMin and SAM. The sedimentology of Vera Rubin Ridge and Glen Torridin suggests that at least portions of both were deposited at the same time in a lake environment about 3.5 billion years ago. But the mineralogy of the 2 are very different, suggesting a different aqueous history. So remember, Vera Rubin Ridge had abundant hematite and also those acid indicator minerals, akagonite and jarosite. But what we see in Glen Torridin is that we don't see any of those acid indicator minerals. We see little to no hematite in these samples. Also on Vera Rubin Ridge, we saw relatively low abundances of phyllosilicates. Here we see abundant phyllosilicate, and based on both SAM and ChemMin data, these suggest that this phyllosilicate is the iron 3+ smectite called nontronite. So the lack of those acid indicator minerals and abundant hematite suggests that those oxic and acidic fluids that interacted with Vera Rubin Ridge did not affect Glen Torridin. We also see an interesting mineral that we hadn't detected before, an iron 2+ carbonate called siderite. And the abundance of siderite and the presence of non-trinites suggests that these minerals were precipitated under a near neutral pH and possibly during a time when the CO2 atmosphere of Mars was a bit thicker to allow for the precipitation of carbonate. And SAM did help us identify siderite as well. And I know I haven't discussed much of the SAM results, but I will say that the SAM team recently did a wet chemistry experiment of samples from the Mary Anning drill hole to derivatize a variety of organic molecules. And so look for those results in future conferences and papers, because that's really important for the habitability of Gale Crater. And so just to sum up, data from both ChemIn and SAM suggest that this portion of Gale Crater, the Glen Torridin, would have been habitable to ancient microbial life. Thanks.